Hello, and welcome to this 8-minute preview presentation released to support our research into wind turbine blade integrity monitoring using millimeter wave radar. I'm Jamie Blanche, and I'm a research associate working for the Offshore Robotics for Certification of Assets Hub at Heriot-Watt University in Edinburgh in Scotland. Working in partnership with the Smart Systems Group and Microsense Technologies Limited, we are located at Heriot-Watt University's Riccarton campus. I am pleased to introduce our research, Asset Integrity Monitoring of Wind Turbine Blades with Non-Destructive Radar Sensing. To provide an overview of the technical challenge, our motivation has been to provide runtime asset integrity data of offshore wind farm networks with a focus on blade structural integrity by offering an alternative to rope access teams, reducing risk to life and the asset in the challenging offshore environment. Our non-destructive, non-invasive, non-contact sensing allows for early detection of critical defects, specifically delamination and water ingress. Delamination and water ingress are inherently internal defects that are not often visible from the asset exterior. Reducing operation and maintenance downtime results in greater asset productivity. Shutting down an asset for inspection is costly, and operators tend to do so only when an asset has externally observable defects, which is sometimes too late to mitigate at an early stage, resulting in costly and time-consuming repairs. By contrast, non-contact internal structural sensing, deployed by drone for example, offers earlier warning of defect onset at a fraction of the operational cost normally associated with asset inspection and defect detection. We have employed the novel application of frequency modulated continuous wave radar in the K-band for analysis of porous composite structures. We have approached this problem using patented microwave sensing methods and applied to several use cases, with our focus on wind turbine blades for this presentation. Key advantages of frequency modulated continuous wave radar are low power, non-contact and non-invasive inspection, proven high sensitivity to water, oil and porosity, and real runtime front-end capable analysis. Wind turbine blades are subject to differing operational loads and defect types. The most common are derived from flexing of the structure during operation and weather abrasion. These are manifested in cracks, delamination resulting in water ingress, spray via offshore conditions, structural deformation, and material loss at leading edges. Specific defect types are grouped into 7 distinct categories. For this demonstration, we have focused on Type 4 defects as internal damage not usually visible from the asset exterior. Our test section of wind turbine blade is predominantly a composite structure of balsa, polymer, and fiberglass laminated layers with some metal components. These are typically lightning conductor cables and tensioners. This structure is typical for most wind turbine types, even the largest with blade lengths of up to 90 meters. Our sample is 1.5 meters long, 90 centimeters high, and 40 centimeters at the airfoil chord, where the polymer main spar can be seen. To present our laboratory results, the image on the left is a comparison of return signal amplitudes in the frequency domain for a healthy section of wind turbine blade wooden core structure versus a section of the wooden core structure exhibiting a Type 4 delamination defect. The x-axis is a distance measurement from the sample, with an interfacial peak observed at bin 5. This corresponds to a target distance of 10 centimeters from the antenna. A residual signal decay consistently lower in amplitude for an observed area of delamination or porosity can also be observed. The image on the right is a dynamic return signal amplitude of water added into the same area of internal delamination within the wind turbine blade structure. The x-axis in this case is time, with 3 milliliters of water added at 3 minutes and 40 seconds into the experimental duration, where a clear signal contrast for even this trace volume of water can be seen. In performing these experiments, we have demonstrated that there exists an increase in demand for non-destructive testing to evaluate the state of a wind turbine blade by removing the need for personnel to operate in harsh environments and far offshore. Deployed FMCW via an autonomous robotic platform or embedded within a structure provides asset inspection solutions that save time and expenditure by detecting defects earlier. We have demonstrated the effectiveness of the sensor to detect surface and subsurface faults within the composite structure. We have demonstrated clear contrast in the return signal amplitude for an area which is classed as healthy against an unhealthy, delaminated section of wind turbine blade. And we have shown the clear detection of 3 milliliters of water ingress when applied to an internal delamination defect not visible from the target exterior. To provide a technical summary, we have multiple previous use case deployments of contrast agent detection in porous media, such as oil or water presence, and the detection of metallic structures in low dielectric materials. Corrosion detection on exposed surfaces or under protective insulation layers. The detection of salt and other surface contaminants, and to augment visual spectrum, simultaneous location and mapping sensors to aid collision avoidance and target identification for robotic trusted autonomy and safety compliance roles. Currently at technology readiness level 6, we have successful operation deployment of salt and surface contaminants, corrosion and wind turbine integrity, successful laboratory tests of internal feature detection in civil infrastructure construction materials. The FMCW sensor has been developed in a ruggedized and tunable sensor capable of mil-spec operation in harsh environments. These include fog, mist, spray, low visibility, and thermal resilience. We have performed multiple successful integrations with autonomous platforms for asset integrity and environmental sensing for robotic navigation and mapping. The FMCW is an emergent technology for frontier use in digital twin applications across multiple sectors. Further work to improve current experiments for material and defect type characterization will include multispectral sensing in the microwave and terahertz bands, where the variation in inspection frequency will inform higher resolution defect types and new measurands. Further integration of the platform-agnostic FMCW sensor suite with trusted autonomous systems will allow improvements in asset management efficiency, saving costs in OPEX and CAPEX while preserving the longevity of the renewable energy asset. We invite you to view our other published research outputs. The research team biographies and ORCA project contact details will follow this slide shortly. Thank you for watching, and we look forward to future engagements.